Yeah, that will send me and say something. Yes. Yeah, it is. It is it's something. Yeah, you're not the key, right? Yeah, I think so. Yeah, that's something. Hey guys, so the recording is started. If you want to say anything offensive, save it for afterward. All right. Yeah, I should have thought ahead. Sorry, guys. Okay, so today we're starting with a new section, which is a good thing because we had a long break, and during that break, we probably forgot all the other stuff we did. It's okay, we don't need it here. All right, so today we're starting with ASCII. I'm hoping you guys did this in another module already. Have you guys seen this before in another module? Okay, maybe you guys will see it at some point. I was hoping you already did it, so I can go through it a bit quickly because it's not difficult. It's just a bit boring. Okay, but we'll go through it quickly. ASCII. So you guys just need to know about this is that firstly, it's an outdated way of doing things, but historically you need to learn it. And so far we've been learning how to represent numbers in binary, positive numbers, negative numbers, adding, subtracting, all of these operations as well. Now we're going to learn how to represent text in binary, so string variables, right? And the way it used to be historically done is it's just straightforward. We just have an encoding scheme to represent every character on a keyboard, right? So something like this. It's quite a big thing. So let me at least show you guys a bit of it. So for example, if you want to code the spacebar key, right, then what do we see up here? Let me point, since we are recording this, I'll point here. This part here is the binary representation of the spacebar key. So if a computer sees this string of binary bits, it understands that somebody pressed the spacebar key. Right, that's all it means. Okay, and every different character on a keyboard has some corresponding binary string to represent it. Right, we see all of these are 8 bits, I think. 2, 3, 4, 5, 6, 7, 7 for some reason. Right, 7 bits. Or we can always make them 8 by adding a 0 to the front. Yeah, I don't know what much more to say about this. It's quite straightforward, right? It's just a different string. They're quite randomly assigned as well. There's like no order in the way these numbers are made. And just different strings represent different characters on a keyboard, right? Does that kind of make sense to you guys? Okay. So that's all you need to know about ASCII. That's what it is. And they give us an example where we need to try to write words using ASCII, which is a bit unnecessary. Let's do at least one of them so we know how to do them. Yeah, so let's say, for example, they ask you to represent the word science in ASCII. What you would do is, okay, so let's just break it up. If you want to write the word science using ASCII, it's SCIENCE. We need to go find the binary representation for each letter here. Right? Are we starting with a small or big S? It's a small s, right? So we look up here for the small s, which is, why is my brain? I don't see any small letters there. On the side. Oh, it's on the side. Thank you. So there we go. This one here. So to write science, let's just do it quickly here. First, I'll write S, which is going to be 111011. Then I'll write C, which is going to be somewhere up here, I guess. 11000. So 11000. 11. Okay, so that's the S and the C, and I'm guessing you guys can do the rest, right? You guys get what I'm doing here. Just filling each letter in. Okay. So let me just make it better. Dot, dot, dot. So that's how we write words. And I doubt this will ever come out, but if it does, they will have to give you this entire table in the exam, and it's very unlikely. So it's unlikely to get a question like this, but just in case it comes out, for record's sake on the video, we are saying we know how to do it, right? Okay. All right. For legal purposes. Yeah. Okay, so that's ASCII. What else do we need to know? Yeah, so before we get to the next thing, one more thing we need to know about ASCII is that you notice it can represent numbers as well, right? If I look at this table, we have numbers here as well, right here, 0 to 9. And notice these are not the same as the actual binary numbers we learned before, right? Because we know a 0 in binary will just be all zeros here, right? But this is a different thing. This is a string 0 as opposed to, what do you guys call it in programming? Integer or double or whatever, right? So this is a string. These are all string variables. So these binary bits next to the numbers don't correspond to the actual number value that we worked out before, right? Does that make sense to you guys? Yeah, it does. Okay. All right, perfect. So all I'm really saying is if I take this one here and add it to this 2, for example, where we do it binary, you won't get 3 as an answer. You'll get some other weird thing. So we can't do arithmetic with these numbers here. These are just string numbers. And this is equivalent to, I think they give us an example here where, let me just check the example here. So you might notice sometimes if you type a phone number into Excel, I'm not sure if you guys still use Excel in this day and age, but if anyone's used Excel and you type a phone number that starts, I'll say that again. If you type a phone number that starts with a 0, Excel will take out that 0, right? It usually does that. Unless you change the data type to whatever string, or I'm not sure what they call it in Excel, we can go and check, but text, right? Thank you. Unless you change the data type to text, then it will assume it's a number and it will remove the front 0 because the front 0 doesn't do anything anyway, right? So just remember, string and number variables are different. So here we're learning about all the string variables. Okay, so that's ASCII. ASCII is quite straightforward. It's just that table. The table is all we need to know. In Unicode, so this is slightly different, slightly more complicated. Now, firstly, why do we have so many different things? Well, ASCII is outdated, right? It's not used because it's good maybe for English, but we have a lot more languages in the world and a lot of different characters and stuff like that. So ASCII is outdated in that sense. And Unicode is able to encode a lot more different languages, a lot of different symbols. If you look at maths and physics and stuff like that, people always use Greek letters, things like that. So we don't have things like that in ASCII. But in Unicode, okay, so in Unicode, we have everything we need. Now, Unicode is broken up into 3 different types: UTF-8, UTF-16, and UTF-32. So already we're getting to subgroups here. And I think the number at the end, yes, the number at the end just represents the number of bits used to represent information in this encoding scheme. So UTF-8 means we use 8 bits, UTF-16 means we use 16 bits, and 32 means 32 bits. Okay, so let's just try and get into something so we can get a bit of a feel for this. It's a bit abstract at the moment. Okay, so here's an example here. Okay. So firstly, we obviously need a lookup table, just like how we have for ASCII. We have some lookup table to tell you what binary string of bits corresponds to each character. Here we need the same thing. And usually we need to get these from the internet. We can Google them or something to get the full list. I found one online. I took a screenshot of it just to show you guys an example of what it looks like. So the spacebar, for example, is the first thing we see right on top here. Spacebar is represented by the number 20 here means it's the 20th item on the list. So that's a decimal 20 right here. So this is a big list, just like what we had for ASCII, but this is much bigger. So this is firstly the label of where we are. This is the 20th item on the list. Wait, hang on. What's this 32 then? 32 in decimal. 20 and 32. Unicode 20. Anyone make sense? Or maybe that's it's like a hexadecimal representation. So 3 and 2 representing a different. Maybe we should check it before I assume things. So that should be kind of like a hexadecimal. So 3. I don't remember. It's been a while for me as well. So do you guys remember how to convert hexadecimal back to a decimal number? We need to first make it into binary, right? And then from binary, we get a number. So if 32 was a sort of hexadecimal type of representation, I'm doing this on the board when we're recording. Let me do it on the screen here. Let's open something up where we can write, or let's just do it here. Okay. So 32, kind of wing it here a little bit. Anyone remembers how to do this? 32, so 3. We need to get 3 in binary first. So what is 3 in binary? 3 in binary will be, this is going down a rabbit hole now. 3 in binary is going to be 3, or let's write it as 2 plus 1, right? We can do that. 2 plus 1, so that's 2 to the 1 plus 2 to the 0. So that is 1, 1, 0, 0. Yeah, okay. So that's 3. 2 in binary is just going to be 2 to the 1, which is just 0, 0, 0, 10. Okay, thank you. Now, once we have this, we can convert this back to decimal, and let's hope it corresponds to 20. Will it? It might. Let's see. Convert this back to decimal, we end up getting, I'll start from the right, 2 to the 0 plus 2 to the 0, 1, 2, 3, 4, 2 to the 4. This is not looking like it's going to be 20, is it? This is going to be too big. 0, 1, 2, 3, 4, 5. 2 to the 5 is what? 32 already, so it's already too big. Okay. So that brings us to the conclusion that I have no idea what this 20 would be.
So, but hexadecimal, hexadecimal 20 is 32 decimal.
Hexadecimal 20 is 32 in decimal. Oh, so I did it the other way around. So I converted 32 from hexadecimal. So if we did it the other way, you're saying if I converted that to decimal, I'd get that.
Yeah.
Okay.
But
Okay, so all we need is the decimal one. Let's not even worry about this, right? We don't need to worry about that. All I'm trying to show you guys, a very simple thing, which is becoming a complicated thing, is that this is just the number of the thing in the Unicode table. So it'll start from 1 all the way up until however many trillion things are in this table. Number 32 happens to be the space bar. Number 33 happens to be the exclamation mark. 34 happens to be the quotation mark, whatever. Right? These are all different possible keys on a keyboard. And not only the keys we know, but different keys from different languages, different symbols, all these things. Right? That's all these numbers are telling us. So what we need to know is these numbers here. That's important. Everything else we can work out from those numbers. The hexadecimal representation, whatever else we need, we can get from that decimal number. Already this video is going to go around and around a little bit, but that's what we needed to know. And here's an example of something that will come up. So if they say, for example, the character H in UTF-32 can be represented by some massive binary string here, which happens to be 72 in decimal, right? So that means that A should be the 72nd entry in a big table like this. All right, so that's what that is telling us. I warned you guys, the section gets very boring, right? So we try not to spend too much of time on it because it's stuff that you can read by yourselves as well. Okay, so that is that. Now let's see, UTF-8 is the simplest one, as I mentioned. Same idea, except it only uses eight bits, right? It's UTF-8. How does UTF-8 work? So this is where we have to, it's the only part we have to really get a bit involved with it. Right, this is where we have to get involved with the table and with how to represent this as a string of binary bits. Okay. UTF-8. Okay, is that, yeah. Okay, so we have a template here which we have to use, and this gets a little bit messy, but let's just do it. So let's go straight to an example, and then we follow the instructions. The 4 steps to follow to convert something into UTF-8 number. So let's see, step 1. Or what's the example? You want to look up the character that looks like this. That character is some, it says Chinese, but I don't think Chinese is actually a language, right? Isn't it Mandarin or Cantonese or something, whatever it is, right? So maybe we're starting a bit of a racist place, which is not good, right? We should specify. Okay, so we're given a symbol and we're saying, determine the Unicode number. You want to find out the representation, yeah. So we're starting with this. So we have to look this up firstly in a table, right? We have to look it up in a table, and that's going to be very difficult because there's going to be no order to the table. So they've done that part for us. If you look this up in a table, you find that this is it 35987. How would it 35,987, how would you say that? Entry in the table. That's where you'd find this. Then you convert that number to binary. Now that's going to be a massive thing to do. You guys can do that, but assuming that's done already, that's shown for us in step 2, what that number looks like in binary. So it's this massive number here. Okay, once you have that number in binary, check how many bits are used to represent the number. So if you count that, you'll see 16 bits. Right? And once you have the number of bits, you have to go to a template. So actually this thing gets very messy. We go to a template, and the template tells us that if you have 16 bits, we use the 3rd line in the template. This is for 16 or fewer bits. Right? So we have to fill in, this is where it gets a bit messy, fill in what we worked out. The binary numbers have to take the places of these X's here. Right? So let's try and do that. Make sure we don't mess it up. So I probably have to take down this template somewhere. Or let's just write on the template. But then I have to bring my binary string bits up here. Okay, either way I have to copy something. Where's the binary bits? It's down here. So the template looked like what? It's 1110. Let's just write it. 1110. And then there are how many places after that? 4. So I'll put 1, 2, 3, 4. Then it's 10 with 1, 2, 3, 4, 5, 6, I guess. Let's just check that. Then another 10 with 6 dashes. So all I did is take down the template. Okay. So again, guys, from the top, having worked out that the Unicode number for what I'm looking for is this. Having converted that to binary, I get this binary string at the bottom. Having looked at the template says if I worked out something to have 16 bits, I use this template up here. Now I need to fill this number into the template above. So do we have 16 places available here? Let's see. Let's just see how it works. So we have 8, we have 6, 12, 13, 14, 15, 16, right? So we have 16, so it should fit nicely. So from which way do we write it? From the right or the left? I have no idea. Let's just do it one way and see if it works. Let's start from the right. I'll fill in. We can check it, right? Let's start from the right. So from the right, it would be 1, 1, 0, 0, 1, 0. Okay, so I've filled in that part. 1, 1, 0, 0, 1, 0. Then I have a 0, 1 left over. 0, 1, this is confusing. 2 zeros and 2 1s. Was it 2 1s? Okay, then we just got 3 zeros and a 1. Thank you. Now, is that correct with what they have at the bottom? Let's check. Looks fine to me. All right, so that was only step 2.
So if you had like 15 or 14, you would put zeros here. Get like what was the
15 or 14 bits, you mean?
But yeah.
Then we'd use a different number, different thing from the template. Oh, yes, yeah,
And
yeah.
then zero.
Zeros in whatever's left, yeah. Right. Yeah. Yeah, that's a good point, actually. Okay. All right, so, okay, so actually it looks like UTF-8 uses a minimum of 8, but it could be more. Could be more bits. Okay, so the name is a bit misleading, so let's just keep that in mind. UTF-8 uses 8 or more bits. Okay, any questions so far? All right, I can see we're just trying to get through this as quickly as we can. Let's get out of the way. UTF-8, 16, sorry, let's read what's the story with 16. So just like UTF-8, UTF-16 is a variable length encoding scheme for Unicode because it's far more complex than UTF-8. We won't explain how it works here. Okay, that's nice. So we're not going to do that. There were 3, though we only did 2, right? So are we missing something? Yeah, that's it actually. 8, 16, and 32. Did you guys see me miss something as we went along here? We only did 1 thing, but there's supposed to be 3 here. And we told we can skip 1. So if my thinking is correct, we're missing 1, right? Let's just check, make sure we didn't skip something. UTF-8. All right, UTF-32. Okay, we kind of did this. UTF-32 is the one which is, let me just say this concretely one time. UTF-32 is fixed length. It uses 32 bits all the time. Right? So again, it uses the same lookup table, the same Unicode lookup table, except it's very wasteful of space. Because, for example, the letter H here, we only need 8 bits. You can see clearly. This scheme always uses 32 bits, so we can see this fills in zeros for the rest. Right, and that's a lot of unnecessary space. Okay, so I can see, guys, it's hard to keep something like this interesting. In summary, just a few things. First thing, UTF-32 is fixed length. 32 bits never changes. UTF-8, the length can change. That's the example we did. It shows you how to change the length depending on the number of bits we work out. And UTF-16 apparently is too complicated for our minds to follow, so that we're not going to learn it here. Right? That's a good thing because I also don't have any idea what that is. Right, so now we can get to the more interesting stuff. Okay, summary here if you guys need. ASCII, UTF-8, UTF-16, 32. 16, we don't want it. We don't care, right? We didn't learn that. We don't care about it. This is maths, right? Doesn't feel like it. You got a physics guy who barely knows maths teaching IT. That's what's happening here. Okay. All right, so now we learn about images and color. This is a little bit interesting because it shows you how we use binary to represent colors on screens, right? And this is how all screens actually work. They all use binary. And generally, we have to know a bit about colors here. Anyone remembers the primary colors and stuff like that? Red, yellow, and blue, apparently, right? Primary colors. So in other words, we can mix these colors to make any other color, right? Red, yellow, and blue. Red, yellow, and blue. And here, sorry guys, I thought I was having a stroke for a moment, but I came back. All right, so what I'm trying to say here is that we actually use red, green, and blue, which apparently we can use to make any color as well. RGB. Sorry? Yeah.
Your primary colors are red, green. That's why you have the RGB scale.
Yeah.
If you're mixing paints and all stuff, then it's green, yellow.
Yellow, blue. Okay. All right. Subtle difference. I guess you can make green with yellow and blue. So somehow these two are equivalent. Okay. All right. Also, guys, just note the word. There's a word here, additive. So additive, right? So in RGB, we usually start with a black screen, not with like a white canvas in painting. We start with the black screen and add colors to that to make any color. So that's why this is called additive. Right, so just take note of that. Again, it's all in the notes. I hope I uploaded LU5. If I didn't, I will do that.
Learning Unit 5 slides.
Learning Unit 5. Actually, yep, we'll probably get to that next time anyway, so it's okay. Oh, sorry, I know that was very random. So anyway, let's get to some pictures now so we can understand this. You know, let's throw this aside for a second and let's draw something. All right, so how does a pixel work? You guys know what pixels are, firstly? All right. Guys, whoever is starting their car, please turn it off. Something disturbing here. Okay, you guys know what pixels are, right? Okay. So a pixel is the smallest unit of a screen, basically. So if one pixel, I wouldn't recommend trying this, but if you were to like put your screen against your eye and look very closely, maybe with a magnifying glass or something, you'd see the pixels. Right? With modern screens, it's getting harder to do that, but you can still see them. They're really tiny, tiny little squares that make up your screen. Anyone's ever done that? Anyone's ever seen a pixel? Right? They're all over, they're all around. Some of you have done that. Okay, all right. I wouldn't recommend it. It's not good for your eyesight, but so suppose this is a pixel right here. Right? Okay. Guys, just a little bit quieter, please. The back. Okay, guys, just a little bit quieter in the back, please. All right, so suppose this is a pixel. A pixel is made up of 3 lights inside them. I'm not going to change colors. That's going to take too long. What did we say? Red, green, and blue. RGB. So red, green, and blue. So maybe let's change the colors, just since make this a little bit colorful. So we have a red light, green light. That's not green. If this were to happen today, that would be nice. Red, green, and blue. Okay, so can anyone try to imagine how using these different lights we can get any color that we want? Yeah, overlap them. So it's so because it's so small, even in the orientation it's okay. But the point I'm looking for is it's a different degrees of onness, you could say. If they're all completely off, the pixel is going to be black. If you start turning the red light on, then you'll get a red pixel. But if you turn the red light on a little bit, then the green light a little bit, the blue light a little bit, you'll get some color in between, whatever they make up. So the different levels of turning them on is what gives you the different colors. Right? And you can imagine this becomes a very complicated web because this is just one pixel. And a screen usually has a resolution of what's like 3000 something times 3000 or something like that. Some of them go bigger than that. That's a lot of pixels, right? That's a big symphony at play to make a picture. That's just a picture, right? Videos become more complicated. All right. So somehow this has to tie into binary. Is it time for the break yet? Not yet. Okay. Somehow this has to tie into binary. So each pixel can represent an onness of level 0 to 255. Right? Does that number look familiar to anybody? 255, right? Can anyone tell me where that number comes from? Looks familiar, but that's about it. Anything else? Have a guess. Yeah, we've seen it somewhere, right? It's definitely. Okay, so the reason this number comes up is because suppose you had 8 bits. I'll represent them here. 1, 2, 3, 4, 5, 6, 7, 8. How many different combinations of possible representations can I have with 8 bits? Right? 256. Right? 256. So every bit, so because it's 8 bits, we get 2 to the power 8, which corresponds to 256 different possibilities. Right? And these different possibilities, basically we can represent numbers from 1 to 200, sorry, from 0 to 255. Right? Those are 256 possibilities. And every number represents a level of onness of the light. Right? So if it's 255, the light is fully on. If it's 0, the light is fully off. So that's why we need 8 bits per pixel to represent the light being on or off in a certain amount.
Why did they say brightness?
I'm not sure. I'm not sure. Shall we change the word brightness? Does it say brightness?
Yeah, there's
Onness, yeah. That's why I'm using this. Anyway, English is not my first language, so I'm just going with it. Oh, yeah, no, I'm joking. English is my first language. Just, yeah, I come from the farm, so it's a bit different. So anyway, guys, so if we need 8, let's just write here, how will I write this? 1, 2, 3, 4, 5, 6, 7, 8. There's another 8 here. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 pixels, 8 bits per pixel. So how many bits do we have per, how should we say this? We have 8 bits per light, I should say. So how many bits do we have per pixel? 8 times 3, right? So we have 8 times 3. What's that? That's 24, right? So have you guys heard of 24-bit color before? Oh, that's a bit outdated for you guys. Okay. So 24 bits, right? So this is 24-bit color. It means every single pixel uses 24 bits to represent something, right? Now, if we imagine a relatively small screen, let's see what sizes they look at here. Let me not go too far off-road. Okay. So RGB color mixes, do you guys want to use them? Actually, we'll do an example like that just now. The 24 bits, we spoke about that. Okay, so if we're to work out how many colors can be represented with, is this a single pixel, 256? Yeah, this is a single pixel, right? So this is a lot of colors. So it's 16 million colors and some change. It's more like 17 million colors if you round it up. And apparently this is more colors than the human eye can perceive. Right? So this is why they sometimes call this true color or real color. Right? It's a strange thing, but a thing that we make can create more colors than can be seen by the human eye. All right. Yeah. Okay, so now we can start doing some actual examples instead of all this abstract stuff. So this is the kind of thing the computer will be given. It will be given a bit of a string of bits that looks something like this, as an example, and the computer needs to interpret that as a color. So how does the computer do that is the question, right? It needs to associate each of these with a color. And do you guys want to try this now or after the break? After the break. You guys want to break? Okay. Democracy, guys, if you want to break now, put your hands up so I can see. Okay. All right. If you want to do the example first, put your hands up before the break. Okay. All right. If you have no opinion, put your hands up. Okay, guys, take a break. Come back at 5 to 11. 5 to 11, not 5 past. Okay. 15-minute break.